class, we're going to start chapter 6, which is about exponential and logarithmic functions. And these are two very special types of functions. They're actually inverses of each other, which is something we're going to be building up to fully understanding the concept of inverse functions. And the first place we need to start is with composite functions. Friendly reminder that the domain of a function is the set of all possible values of x, and the range of a function is the set of all possible values of our dependent variable y. Remember that a function can be defined as a relation, a set of ordered pairs, an equation, right? And a function is a relation in which each x has exactly one y value. So what does that look like? Well, let's think back to our vending machine, right? This is the first way I started talking about what a function was. So with your vending machine, you've got your inputs, which are its buttons, right? Like C6, E7, D4, and we've got our outputs. That's our snacks, right? So we've got M&Ms, we've got a Coke, we've got an apple, because we pretend to be healthy, but we know nobody's buying that apple, right? Let's go ahead and talk more about how this vending machine works. If I push C6, I get M&Ms. If I push E7, I get a Coke. If I push D4, I get an apple. Cool. This vending machine works. Each x has exactly one y. This vending machine would still work. Let's draw another vending machine. Let's change colors. If I had C6, E7, D4, M&Ms, and Coke. My vending machine would still work if C6 went to M&Ms, E7 went to M&Ms, and D4 went to Coke, right? I push my button, I get out one snack. I push my button, I get out one snack. It doesn't matter that these two x's have the same y. Each x has exactly one y value. So both of these are functions. Let's talk about an example of a non-function, right? So for my vending machine to not work, if I have C6, E7, D4, M&Ms, Coke, and an apple, right? If I have C6 going to M&Ms, C6 going to Coke, and D4 going to apple, if I push C6, what's going to happen? Well, my vending machine's going to break, right? It doesn't want to give you the Coke and the M&Ms. You only paid for one. So this is an example of something that is not a function, right? Our vending machine quits to function if we had one button programmed to two different snacks. One way to test if something is a function is if every vertical line intersects the graph of a relation in no more than one point, right? So if it passes the vertical line test. So for example, all lines of the form y equals mx plus b are functions. All quadratics of the form y equals ax squared plus bx plus c, right? That's quadratics. We learned about those in chapter, I don't remember exactly what chapter, but we have talked about them before. Some examples of things that are not functions would be a rotated parabola or a circle. If I have two functions and f and g are both functions, I can compose the functions by substituting in g of x into f of x. So instead of having f of x, we've got f of g of x. In the domain of f composed with g, that's how we say this. We say this f composed with, it's not times, so be careful. F composed with g will be the set of all numbers in the domain of g such that g of x is in the domain of x. What does that mean? Well, we're going to work through some examples as we go through this section. So let's first start by practicing composition. I always rewrite my function composition. Let's switch to a less angry color. I always rewrite my function composition as f of g of x, right? Because that kind of gives me a clue that I'm substituting g of x into f. So f of x is x squared. But I'm substituting g of x in for x. So that's going to give me x plus 3 squared. Well, I can't just distribute that square. I've got to FOIL it out. So I've got x squared plus 6x plus 9. Now, if I went to find f of g of 2, I can do that in two separate ways. So one, now that I know what f composed with g of x is, I could substitute in 2 into that function. And I'd get 2 squared plus 6 times 2 plus 9, which is 4 plus 12 plus 9, which is 25. The other way is if I wanted f composed with g of 2 and I hadn't already found what the two functions were composed, I would have f of g of x, but not x2, f of g of 2. So that means I'd have f of, what's g of 2? Well, that's 2 plus 3, which is f of 5. Well, f is x squared, so 5 squared is 25. I would get the exact same answer, which is pretty darn cool. For our next example, let f of x equal 4x minus 1 and g of x equal x squared plus 5. This time I went g composed with f. So that's going to be g of f of x. Now I'm going to be substituting f of x in for x in g. So I have 4x minus 1 squared plus 5. 4x minus 1 squared is going to be 16x squared minus 8x plus 1 plus 5. So I have 16x squared minus 8x plus 6. Again, if I went g of f of 2, negative 2, I could either substitute in to my previously found function composition, or I could take g of f of negative 2. So I'd substitute negative 2 in for 4. And my oven's preheated. In case you heard that dinging, that's me roasting some chickpeas, because I'm apparently that person now. But they're really good. I covered them in tahini. So if I take g of f of negative 2, that's 4 times negative 2 minus 1. That's g of 4 times negative 2 minus 1. I'm substituting in for f. So that gives me g of negative 9. Well, that's going to be negative 9 squared plus 5, which is 81 plus 5, which is 86. What I want us to get really good about is what the domain of our function composition is going to be, right? So given two functions, f and g, if I compose them, then the domain of my composite function is the set of inputs for the domain in g, for which g of x is in the domain of f, right? So we really depend more on what the domain of g is. So for example, here I have f of x equals x squared plus 1 and g of x equals negative 3x plus 2. The domain of f is all real numbers. Remember, this is a graph of a parabola. It looks like this. And its domain's all real numbers. The same is true for the domain of g. It's a linear equation. Its graph looks like a line, but the line has negative slope. So let me at least draw it head in the correct direction. Negative slope. So it goes from negative infinity to positive infinity. So the domain of my composite function would be negative infinity to positive infinity. Now let's take a look at f of x equals x squared. Well, f of x would have a domain from negative infinity to positive infinity. G of x is the square root function, right? I can only take the square root of positive numbers. Its domain goes from 0, inclusive, to positive infinity. So if I compose f with g, I have to take all the values in the domain of g that are also in the domain of f. Well, that's just going to be 0 to positive infinity. Things get a little trickier when we're looking at rational functions. So if I have f of x equals 1 over x, its domain is all numbers, except where x equals 0. If I look at g of x equals 3x over x squared minus 1, its domain excludes the numbers if I was to factor this and set it equal to 0. Its domain is all numbers except where x equals -1 or 1. So the domain of my composite function might be a little hard to see. So let's go ahead and compose these two. If I take f composed with g, that's of x, that's f of g of x. That's going to be one over 3x over x squared minus 1, which would just give us x squared minus 1 over 3x. All right, so 0 can't be in its domain, but neither can -1 and 1. So the domain of f composed with g is all values of x except where x equals -1, 0, or 1.